All right, everyone, welcome back. This example will again be on conservation of angular momentum, but it'll be slightly different than in previous example videos. So the problem situation is we have a long rigid rod right here of length, we'll say L, right? It's fixed about a pivot point at the center, so that effectively acts as its axis. This is kind of a top-down view, okay? So gravity plays no part here. We have a projectile fired with some initial velocity at an angle of 60 degrees, and let's see, initially it travels like that, right? That's the only thing that's moving. After the collision, though, it lodges and sticks into the end of this rod, and then the rod and the projectile as one rotate counterclockwise. Okay, so this is effectively a collision problem, and because there's rotation, it's an angular momentum problem. Okay, we don't, though, have to have rotation both initially and finally, right? Both before and after the collision. In this case, we just have it afterwards. Okay, so this is a conservation of angular momentum problem. So Li equals L final, and this may resemble some examples previously, in that before the collision, there's no rotation, so the angular momentum can be written as R cross P, right? That projectile has some velocity v with a magnitude of, v, and that's what we're trying to find, right? We want to find the projectile speed just before impact. So just before is just right there, okay? So there's an angle embedded in that R cross P expression, so I'm going to translate the bullet such that it's, say, right about there, just before, and the velocity vector translated up is there, okay? So we need a radius, right? We need the R vector, and so we need a point of reference, in other words. I choose the axis, okay? Because I think that's the simplest. So let's go from the axis to where the projectile is just before impact. So let's effectively go right there, right? That means if we were to extend R, we have an angle theta right there, and that's the same as the angle shown, okay? I know it looks like the R vector is not pointing towards the bullet exactly. I know, just kind of assume that it's close by, right? That change, right, that's the real vector. Well, the difference between that and that is pretty small, okay? So let's just say that it's R cross P, and the magnitude of that we'll evaluate in a second. All right, let's go back there. All right, initially, angular momentum, R cross P, as measured from the axis. After the collision, both bullet and rod will be rotating as one system, right? So because of that, and the fact that the system will be rotating through the axis, which is located at the center of mass, we can write the angular momentum as I omega. Right? So actually, let me do it like this. Right? The total moment of inertia times the common final angular speed. And so there's really two objects here. There's the rod. So I'll say the moment of inertia of the rod plus the moment of inertia for the bullet. And they both rotate with a common omega final. There we go. All right. So the speed that we're trying to find before the impact, right, is embedded in there. So let's evaluate that. Magnitude of this is R mv sine theta. And then afterwards, let's see, the moment of inertia of a rigid rod rotating about the center. If you look back at your table in chapter 10, that should be 1/12 times the mass of that rod. Let's use capital M times L squared. Do I have a length? I do. I'll just say it's L squared. Plus the moment of inertia for the projectile, which can be effectively assumed to be a point particle. So located right here, the point particle from the axis is mr squared. And that r, by the way, is, well, L over 2, right? L over 2 being half of the rod. And so all that times the final angular speed. All right, so what we wanted to solve for, V, is right there. I think we know it, everything else. R, M, right? The magnitude of R is just L over 2. I plugged it in there, but not here. Let's do that now. So 1/12, the mass of that rod is 4.7 kilograms. L, the total length, by the way, is 0.27. Plus the mass of the projectile is 0.34 kilograms. That's at a distance of L over 2, which is 0.27, let's say 0.135 squared. All that times the final omega, which is there, 9 radians per second, SI units. And divided by Rm sine theta. So in this case, our value for the radius was L over 2, right? Which I had over there, which is the same as 0.135 times the mass, and that's lowercase m, right? By the way, this here is the linear momentum for the only object that's moving before the collision, and that's the projectile of mass lowercase m, which I have as 0.34. Whoops. And then sine of, in this case, theta is 60. So everything is in SI units. Notice it has to be, the omega here has to be in radians per second because we're solving for a speed that's in meters per second, right? In a previous example, I had omega in revolutions per second, and I kind of left it in those units. That's because I was solving for another omega, and it ended up in units of revolutions per second, so it worked out. Here, we have to use SI units to get SI units of meters per second for the speed v. Okay? So we should get a final answer of about 7.87 meters per second. And that's the initial speed of the bullet right here before impact. Okay? So this was another example on the conservation of angular momentum. It was a collision problem. It was a collision problem with rotation. Okay, so we kind of synthesized the angular momentum before the collision that did not have rotation. Because of that, we used the expression for L as R cross P, and we equated that to after the collision, both objects were rotating about the center of mass, and because of that fact, we use the form of I omega. Okay? We don't always have to use I omega initially and I omega finally. Okay? So, thanks for watching.